Hi there. I'm glad you made it here. Settle into the hush of your room, the lamplight, the steady tick of the clock, the kind of quiet that holds you like a soft blanket. Let your shoulders loosen. Let the day step gently to the doorway and wait outside. Tonight, we're going to wander the starfields with unhurried steps and ask a simple, tender question. How did we misunderstand galaxies for so long? For years, we squinted at the spirals and thought we knew their rhythm. Then New Eyes Gaia, mapping the sky in fine detail, Vista, peering through dust, began to show us hidden threads, young stars tucked in a thin, secret disk near our Milky Way's heart, streams from old mergers folded into our night, and distant beacons, quasars, whispering of colossal engines in the dark. We'll drift through those ideas as if walking a quiet shoreline at dusk, no rush, just the sound of waves of starlight coming in. If these calm journeys help you rest, a gentle like and subscribe will quietly help other sleepy travelers find this space too. For now, breathe the easy air of evening. The spiral arms are waiting, patient as time. Let's begin. Strange, isn't it, living inside a city of stars and still not knowing its streets? From our small porch of night, even the basics blur a little. How many lights are in this town? Some counts whisper 100 billion. Others swell to 400. The spiral we call home, is it sketched with 2 grand arms or 4? The picture keeps shifting like moonlight on water. Looking outward is easy. Looking from within is a tender kind of guesswork, like trying to sketch your own house while standing in the hallway. There's a quieter question too, one that pads in on soft feet. How many galaxies hide inside our Milky Way's story? Over a decade of steady watching, Gaia has traced the faintest tremors of starlight, trillions of tiny measurements, patient as breath. In that hush of data, about 30,000 stars ripple against the stream, moving the wrong way, as if they remember a different river. They are migrants from long-ago visitors, the crumbs of swallowed galaxies folded into our sky, memories carried in motion. Part of the trouble is the dust-laced plane of our galaxy itself, thick with gas and stars that pile up toward the center. Astronomers have a gentle name for the blind spot it creates: the zone of avoidance. Visible light surrenders there. The view becomes a warm, opaque curtain. So we lean on other ways of seeing X-rays, longer waves that slip between grains of dust, windows that open where the usual ones are shuttered. It's the house again. We stand in our bedroom, pressing an ear to the wall, learning the shape of rooms by the echoes of our own quiet. Distance complicates everything. A nearby ember can glow as softly as a faraway beacon, without a sense of how far the map smears. Some stars, blessedly regular, pulse like faithful metronomes and tell us who they are. Others keep their secrets. For the stubborn ones, Gaia trusted something simple and deep: parallax. Imagine holding a fingertip in front of your face and gently changing which eye you favor. The fingertip seems to step sideways against the room, a tiny dance that tells you how close it is. Scale that up to Earth itself, circling the sun every half year. We stand on the far side of our orbit, and the sky bends by a hair. Stars trace minuscule loops, not because they wheel that way, but because we do. With a little trigonometry and a lot of patience, those loops become distances, the way a heartbeat becomes a rhythm. There's a slower drift layered on top of those loops, the proper motion of stars themselves, each one sliding across the black over long years. Nearby stars draw a more noticeable thread, Distant ones shift like the hour hand on a sleepy clock. Fold these motions together and depth appears, a three-dimensional hush where the Milky Way's lanes and bridges start to show. 2 billion stars now sit in that evolving atlas, not the whole ocean but a generous bay, detailed enough for currents to become visible. Gaia listened not only for where stars are and how they move, but for what they are made of and how they shine. Twin telescopes feed a camera with almost 1 billion pixels, a net fine enough to catch the smallest tremor of light. A spectrometer reads the Doppler hum, the subtle reddening or bluing that tells whether a star is coming or going along our line of sight. Photometric eyes weigh brightness in delicate colors, teasing out temperature, mass, the fingerprints of elements forged in ancient fires. When these measurements are layered over time, the map becomes a living thing. Stars rising and falling, streams uncoiling, histories playing back at a pace meant for dreams. That's how the backward travelers revealed themselves. 30,000 little rebels flowing upstream. Their paths point to past meals, dwarf galaxies tidally folded into our disk, their stars keeping the accent of their birthplace long after the borders disappeared. Somewhere in that folding, the question of spiral arms grows softer. Two or four, perhaps the answer changes with the kind of stars you watch. Young ones threading a thin, secret disk near the galactic heart, older ones strewn wider like autumn leaves. From the ground, it's easy to mistake crowding for structure, fog for form. From Gaia's unblinking seat in space, the fog thins and patterns emerge with the patience of tide marks. Even so, some rooms in the house remain dim. Dust still braids the midplane. Bright giants masquerade as nearby dwarfs until their colors give them away. The far side of the galaxy drifts like a faint shoreline beyond mist. Yet, the longer the watch, the clearer the pulse. Measurements made again and again. 3 trillion quiet taps turn noise into a lullaby of certainty. In that music, the Milky Way's appetite is not a rumor, but a record. Streams of stars arcing like silk, moving against the grain, spelling the names of lost companions in motions rather than words. So we keep tracing the arcs, letting new eyes infrared, radio, X-ray slip between the curtains, while Gaia's ledger of positions and velocities grows deeper. The city of stars we call home is still a work in progress on our bedside table, lines filling in as the night goes on. Somewhere between the hush of dust and the glitter of arms, between 2 and 4, between 100 and 400 billion, the truth keeps breathing. And as it breathes, the old misunderstandings loosen, untying like knots in a ribbon, until the whole shape of our house feels a little clearer, and the hallways invite us to wander without hurry. And in that same quiet, a patient sentinel has been at the window since 2013, breathing in starlight and setting it down, line by careful line. The longer the vigil, the steadier the script. Time widens the parallax, the way a slow, deep breath opens the chest. Its notebooks have arrived in gentle waves. 2016, 2018, a slimmer parcel in 2020, and a fuller, richer volume in 2022. With enough pages spread across the table, the Milky Way's pattern softens into focus. No spacecraft has stepped far enough back to take our portrait, so we stitch one from this ledger, Gaia's notes, woven into a likeness whose edges ripple like wind on a pond. Those small tremors are histories, and together they turn our house of stars into something we can trace with unhurried fingers. Wind the motions backward, and the clues line up. In a sweep of 7 million stars, about 30,000 drifted the wrong way, colors and brightness a little off, like shells from a different beach. The best story that fits their paths is an ancient meeting, a small galaxy plunging into ours 8 to 11 billion years ago. Astronomers sometimes call that guest Gaia Enceladus, or the sausage, a name as odd and endearing as the universe itself. For a while, its stars kept their shape, a red thread visible in the weave, then spread, braided into the disk. That encounter may have nudged our Milky Way into wearing a central bar, a luminous handle that about 2/3 of spiral galaxies carry with casual grace. It wasn't a single midnight snack. Evidence points to other meals, another small companion, perhaps paired with Gaia Enceladus, and later still, hints that as many as 6 dwarfs were gathered in and folded into our lanes of stars. One of them we can still see mid-embrace, the Sagittarius dwarf, which has already brushed past us 3 times in the last 4 to 5 billion years, and will wander through again. That passing may have sent a wave through nearby gas, the kind of ripple that sparks star birth, the kind that eventually could lead to a sun and a set of small worlds where someone might be listening, drowsy and curious, late at night. The watcher itself has grown quiet, held steady at the Sun-Earth system's second Lagrange point. It trimmed its position with cold gas, a careful 12 grams a day, like a lighthouse keeper rationing oil. The tank finally ran dry. On the 15th of January 2025, it took a last look. By March 27, the instruments were easing into silence. The pages it left behind are far from finished. Another delivery is on the way, Data Release 4, expected in 2026. A 5.5-year slice rendered at astonishing detail, about 500 terabytes of sky. In those measurements, the tiny wobbles of starlight may betray unseen companions, sketching hints of exoplanets, and the catalog of binary stars will become the largest we have. With enough motion recorded, the map can be played forward as well as back. Nearby stars drift apart across the Milky Way like friends taking different streets, only to find themselves drawn together again by density waves, subtle traffic patterns in the disk that carve the spiral shape we see. Watching that choreography unfold in models turns the idea of spiral arms from a diagram into a slow dance you can feel. Closer to home, the same calm attention sharpened our view of small, tumbling stones. Positions and directions for over 150,000 asteroids were pinned more precisely, and faint wobbles in their paths suggested something many of them keep: companions. 352 likely binaries, asteroids with moons nearly doubling the number we knew, tiny couples circling in the dark. Far beyond, the ledger of distant beacons grew huge, about 1.3 million quasars mapped into a 3-dimensional tapestry, some from an era when the universe was just 1.5 billion years old, their light traveling almost the entire age of everything to reach us. Even here in our neighborhood, a new kind of heavy heartbeat appeared, a black hole, roughly 33 times the mass of the Sun, only about 2,000 light-years away, larger than the usual local suspects, and the first of its size found so near. Plans are already whispering in the wings. A successor tuned to the infrared Gaia near would look through the dust that veiled so much of the midplane, extending the baseline of parallax across decades. If it flies, the target year is 2045, far enough ahead to feel like a promised letter. And before that, one more great bundle from the first mission, Data Release 5, tentatively due by the end of this decade, gathering the full 10.5 years into a single, luminous archive. The work feels like sitting by a window at night, watching distant headlights glide along a ridge road. Each pass teaches your eyes a little more about the curve of the hills. Misunderstandings loosen, shapes settle, the mind drifts. In the slow turning of numbers into pictures, and pictures into story, the Milky Way becomes less of a rumor and more of a place still vast, still mysterious, but closer, like footsteps in the hall of a familiar sleeping house. Slip your gaze from that night window to the glossy keepsakes we treasure of far-off star cities, pinwheels and scalloped shells, color washed over darkness like paint thinned with water. Because the pictures don't move, the mind kindly supplies motion, a neat pirouette, the whole thing turning like a polished coin on a tabletop. Comforting, yes, and not quite true. A galaxy isn't a single plate. It's a cosmic flock, millions to trillions of stars tracing their own ellipses, most flowing in the same general stream yet never bolted together. If the disk really spun as one rigid piece, angular momentum would twist those luminous arms into ever tighter coils, corkscrewing the pattern with each turn. That tightening never appears. Across long ages, the arms keep their easy openness, which tells us the grace we see isn't just matter spinning, but a softer choreography patterns moving through the crowd, a slow wave the stars slip into and out of while the shape endures. The leading explanation breathes like surf, density waves. Think of a pattern drifting through the disk, not racing ahead, more like a slow tide line. The arms are places where orbits crowd for a while. Stars and gas move into the pattern, linger in its embrace, and slip out again. The shape endures, even as the cast changes. There's also the bruised weather of a galaxy to consider: supernova shock fronts and strong stellar winds from hot newborns that squeeze gas into ribbons and knots. Compression triggers star birth along the lanes, brightens the arms, and can reinforce the wave. None of this has to be either or. A living disk can carry both the steady hush of a wave and the sudden push of blasts and winds braided together into the long spirals we see. What stirs the wave in the first place is often the disk's own gravity, nudged by a disturbance, a passing companion, a bar at the center, a lopsided clump. Anything that tugs the orbits can set off a pattern. Stars pull on stars, orbits cross and cluster. Over time, a repeating arrangement appears where the paths crowd most. The universe loves rhymes, and we can hear the same one closer to home. Parts of Saturn's rings show spiral density waves. 2. A patch that looks like the cross-section of a tree trunk is, in truth, a very tightly wound spiral, each turn pushed into place by the steady tug of small shepherd moons. Picture an old vinyl record, grooves packed together so closely they look like one tone, while the needle follows a path that never tightens or loosens. A galactic arm held by a pattern with its own measured pattern speed behaves much the same, staying graceful instead of knotting itself into a spiral too tight to breathe. Inside these luminous lanes, the raw material of stars, gas, and dust collects and thickens. The result is a band of nurseries, rosy hydrogen clouds lit from within, clusters being born like lanterns lifting through fog, short-lived O and B stars blazing blue-white before they even get a chance to wander far. The arms shine more than the spaces between, not merely because there's more starlight per square mile, but because the light there is so young and hot. Those brightest massive stars burn through their lives quickly. By the time the drift has carried them out of the arm's denser region, many have already faded in supernova, seeding the gas with heavier elements and stirring the next generation to life. The arm glows where the wave presses, a perpetual springtime pinned to a moving weather front. Another rhythm runs underneath, and it belongs to dark matter. Leave dark matter out, and the outer parts of a galaxy would rotate more slowly than the inner, as the pull of visible mass dwindles with distance. Instead, the outskirts keep up rotation speeds, stay unexpectedly high, often flattening rather than falling. The simplest reading is that an unseen halo of mass extends far beyond the bright disk, adding gravity without adding light. Dark matter doesn't scatter or glow. It makes itself known by shaping motions, by holding stars in fast lanes farther out than luminous matter alone would allow. There are alternative ideas that try to modify gravity's rules to explain the same curves, but they would ask us to rewrite some of the book we use for everything else. For now, the halo picture fits a great deal of what we see. Clues arrive with time as well as distance, and the sky gives both. Light from very remote galaxies started traveling when the universe was much younger, so their dynamics carry a different balance of matter and motion. Many faraway disks show slower outer rotation than nearby cousins, hinting at how mass was arranged earlier on and how turbulence and star formation were jostling the works. The effect tends to scale with how deep in time we're looking, small differences adding up like footfalls on a long path. Patterns are never perfect though, and the cosmos enjoys its exceptions. Some spirals break the rule in ways that feel like a riddle. A rare case like NGC 4622 shows leading outer arms, arms that appear to point in the same direction the galaxy rotates. At first glance, this was hard to accept. Spirals were supposed to trail, then fainter inner arms were traced, and the story tilted into focus. A past encounter likely upset the symmetry and resculpted the lanes, leaving the outer pattern offset from the inner, the way a gust can push a wind chime out of step with its neighbors. Another troublemaker wears a bruised beauty mark, the Black Eye Galaxy, also called M64. There, two disks of material interleave, an inner disk, dusty and defined, turning one way, and a broad ring of gas outside rotating the other. The stars in that outer region don't seem to rebel. It's the gas alone that flows backward, as if poured in more recently from the intergalactic medium, or captured in a merger with a gas-rich companion. Over time, friction and shocks between counter-rotating gas can ignite star formation or gradually settle the mismatch. But for now, the two motions coexist, like rivers crossing in the dark. Spiral isn't the only way a galaxy can hold its light. Ellipticals glow like swaths of frost, rounded, smooth, and built mostly of older stars. The dust and cold gas needed for new suns have been used up or driven out. The factories are quiet, the blue lanterns gone. In these systems, the stars don't share a preferred lane around a common disk. Their paths are more like the overlapping loops of a stirred swarm, bound by gravity, but not aligned. A city of elders, walking in many directions at once. Between these families sits a ghostlier kind, lenticular, the S0 class. A disk remains, a suggestion of rings, sometimes a faint bar, but the arms lack crisp definition. Star formation has slowed. The scaffolding of young light that once outlined spirals is thinning. You can watch a spiral's character blur into lenticular when the supply of cool gas dwindles and the wave no longer lights up its passing. It's a reminder that the arms we admire are not only geometry and gravity, but also fresh fuel and newborn heat. Even when the arms dim, the map isn't finished. Much of a galaxy's story hides behind dust, especially along the midplane where clouds stack and tangle. Visible light, our usual candle, scatters there and fades. Longer wavelengths step in like soft-footed guests. Infrared can slip between grains, warming them and coming through to meet us. That's where a southern sentinel becomes invaluable. The Visible and Infrared Survey Telescope for Astronomy, VISTA. With mirrors tuned to see past the soot, it drew an immense portrait in near-infrared bands, a survey of the Milky Way's bulge and plane that peered through the fog and found riches behind it, more than 1.5 billion objects cataloged across the hidden lanes. There are newborn clusters tucked in cocoons, elderly red giants standing like embers in ash, filaments of dust traced by starlight we'd never seen from the ground before, and distant galaxies peeking through gaps in our own. Infrared maps like these don't just reveal, they connect. Regions that looked like blank walls become doorways. Structures guessed at in radio or X-ray line up with stellar streams we can finally trace with eyes that notice warmth. When the Milky Way's arms are viewed this way, the pattern feels less like paint and more like weather lanes of compression lined with nursery lights, bridges and spurs where gas has been pulled and teased by magnetic fields and shear. Even the emptier patches between arms become interesting. Calmer seas, where long-lived stars cruise and where faint ripples from past encounters still roll, subtle as a sleeping breath. The more we listen, the more the rotation of a galaxy becomes a layered song. There is the steady bass of the dark halo, holding the outskirts in a wide embrace, the mid-tempo of the disk, where the pattern turns at its own measured pace, the bright, quick notes of star-forming regions flaring along the arms, and the soft percussion of shocks, winds, and supernovae that keep stirring the gas. Exceptions add grace notes leading arms here, counter-rotating gas there, reminders that history matters, that mergers and accretion write their signatures in motion. Ellipticals hum a different tune, pressure-supported rather than rotation-led, while lenticulars hover between, a memory of spirals wearing a quieter face. All of this returns us to those still photographs and invites a slower way of seeing them. The arms that look frozen are patterns drifting like dunes. The bright knots are short-lived children lighting the path as they pass. The dark lanes are not emptiness but curtains, and behind them, infrared eyes have found a city of hidden rooms, more than 1 billion lights we couldn't count before, now pinned to a map with the tenderness of patient cartography. The sense of rotation you carry after that isn't a simple spin, it's a gentle drift through lanes of memory, a calm river curving around an unseen shore, the kind of motion you can feel even with your eyes closed. Listening to the universe turn. Out of that quiet music, a map began to breathe open in the dark, not inked, but warmed into being. A different kind of portrait of the Milky Way gathered itself this way, patient, hushed, season after season, until you could lift it to the night and read its relief, like fingertips over braille. The craft was modest and steady, countless small glances laid one over another, until the image settled, edges came clean, and the haze between stars thinned to a gentle veil you could see through. No trumpet call, no bright banner, only a long, faithful gaze slowly maturing into clarity. Far in the Atacama Desert, where the air is thin and the nights are clean, a wide-eyed telescope kept watch. Its name is Vista, part of the European Southern Observatory's outpost at Paranal in Chile, a place built for listening to starlight with as little interference as Earth can manage. Over 13 years, 2010 through 2023 teams gathered on 140 nights and let that listening run. About 200,000 images were taken, each a tile in a mosaic that would eventually spill across the central plane of our galaxy. The ledger grew to 500 terabytes, a weightless mountain of moments. If you streamed a single 4K video until you reached that same amount of data, you'd sit with it almost 3 years without stopping, the way a coastline takes time to walk and truly know. What sets this watcher apart is not just where it stands, but what it can notice. Most telescopes are tuned to visible light. The rainbow our eyes evolved to see roughly from 380 to 700 nanometers. The galaxy, generous and stubborn, hides much of itself behind dust that scatters that kind of light like fog scatters headlights. Vista leans into longer waves in the near-infrared between about 900 and 1,200 nanometers, where photons slip between dust grains instead of bouncing off them. In those wavelengths, the curtains part. Stars swaddled in soot show their faces, cool brown dwarfs. Failed stars that glow too faintly in visible light stand out like embers under ash. An instrument called VirCam takes these warm-toned snapshots, not in a single glance but with an array that stitches together broad fields, revisiting them again and again to catch what changes and what stays. The difference between seeing and seeing through becomes obvious when you put two images side by side. In the Lobster Nebula, NGC 6,357 visible light gives you a dazzled view, rose-colored hydrogen lit by young blue suns, lanes of dust like brushstrokes. It's beautiful and a little secretive. Shift to the infrared and the texture changes. The smoke in front grows transparent, and behind it, a dense city of stars appears. Hundreds of thousands, maybe millions, pricked into view. Hidden rooms light up. Structures you could only guess at become corridors with depth and direction. It's not that the dust is gone. It's that the light you're using has learned how to move through it. The program that shaped this map wore an old name. Via Lactea, Latin for the Milky Way, became an acronym on the sky. VVV, variables in the Via Lactea, paired with VVX, an extended survey that widened and deepened the coverage. The focus was simple. Watch large swaths of the bulge and inner disk, measure brightness with exquisite care, and return often enough to notice when stars change. Variability turns out to be a gift. It can tell you distances, ages, motions. It can flag stars that act as yardsticks and others that act as alarms. More than 300 scientific papers have already spun out of this work, and the map itself, nearly 80% of the Milky Way's luminous mass in infrared, becomes a kind of atlas for everyone else to use. The numbers have a hush to them, a central region catalog deeper than any before it, a sky area equivalent to 8,600 full moons. Roughly 10 times more objects than the best comparable infrared map from 2012. Accuracy is not only in the count but in the depth. The inner galaxy, once blocked by dust, now has a measured shape in 3 dimensions rather than a silhouette. If you could float above our home and look down, you'd see a thickened center, the nuclear bulge rising out of the disk like a lantern. with long lanes curling away. The survey didn't try to chart the whole sky. It held its gaze on that crowded plain, where the dust is densest and the star fields not tight. In the footprint diagrams, small red squares mark places the original program studied, then studied again in the extension, and other colors mark new regions added later. You don't need the picture to feel the logic. Focus where the story is richest, where new stars are being made and old streams cross, where the gravitational traffic is thick. Concentrate on the city center and the highways that feed it. As the data poured in and the images accumulated, a sense of scale came with it. The leader of the survey, astronomer Dante Miniti, has said in many ways that the view has changed for good, and you can feel why from the way surprises keep turning up in the folds. One of the early highlights came in 2015 when the telescope lingered on Messier 20, the Trifid Nebula, about 9,000 light-years from here. In visible light, the Trifid is a pageant, pink emission, where hydrogen is ionized by youthful stars, a halo of scattered blue around the brightest, dark lanes carving the cloud into petals. Switch to the infrared camera and the scene rearranges. The petals become windows. You can see past the local glow and, by luck, catch objects far behind it on the other side of the galaxy that nobody could pin down before. Two of those distant lights turned out to be Cepheid variables, their reddish tint, a sign of how much dust lies along the line of sight. In the image, they look as if they sit just beyond the Trifid's edge, but geometry tells a different story. They are roughly 7 times farther away than the nebula that seems to frame them. It's a neat trick of perspective, a mountain appearing close to a nearby tree because your sightlines happen to overlap. Cepheids carry their own special music. Their brightness breathes in and out over days to months, and that pulse ties tightly to their true luminosity. The rhythm is the key. Once you measure the period, you know how bright the star really is. Compare that to how bright it appears, and distance falls out like a solved riddle. Astronomers call it a period luminosity relation, and the person who first wrote it into a clean law over a century ago was Henrietta Swan Leavitt, quietly measuring Magellanic Cloud stars until a pattern announced itself. Variable stars as a class have been part of our awareness for a long time. By the early 1600s, observers were already realizing that not all stars hold steady. Omicron Cetimira was called a nova at first, a new star appearing out of nowhere, until Johannes Hevelius and others noticed it brightened and dimmed in a cycle of roughly 11 months. Mira isn't a Cepheid. It's a long-period pulsating giant of another family. The point is that change in starlight, once an oddity, became a tool, with Cepheids in particular. The tool is so precise that it stitched together the first reliable steps of the distance ladder, the way we hopscotch from nearby stars, measured by parallax, to galaxies far beyond any hope of triangulation by geometry alone. The two Cepheids peeking through the Trifid add a pair of pins on the far side of the bulge, precious because that region is hard to measure and because every good pin tightens the whole map. Further in toward the center, the survey's long patience paid off in a more dramatic way. A team combed through the bulge fields and flagged 655 candidates that pulsed like Cepheids. Not all Cepheids are the same species. Some are classical, young, massive, freshly minted from thick clouds, and others belong to a more ancient population with a slightly different beat. Sorting the list revealed that 35 of those bulge objects were classical Cepheids, a surprise given that the bulge has generally been considered the province of elders, stars 8 billion years old or more. Pulsation periods and colors put ages on them, and the result came out tender, all under 100 million years, some as young as 25 million. Set that beside our sun's 4.5 billion years, and the comparison feels like a whispered aside. The youngest of those is about 0.6% of the sun's age, no more than a deep breath on the timeline. Youth in that neighborhood implies fuel and compression. It tells you there are places in the inner galaxy where gas still pools and densifies enough to spark starbirth, despite the overall impression that the bulge is a quiet zone of elders. It hints at thin structures, a thin disk of young stars slipping through the central regions that infrared mapping can catch, even when dust would hide them from ordinary view. Finding 35 may not sound like much in a city of billions, but the statistic isn't the point. The existence is. It means the story is layered, old stars tracing the thick history of mergers and tides, and young ones writing fresh lines on the same page. The mechanics of making such a map are mundane and beautiful. Tiles must be planned to overlap so that seams vanish when stitched. Images need careful calibration so that one night seeing matches another's. Detectors with their own quirks must be coaxed into behaving like a single eye. Infrared skies glow and change with temperature. Subtraction is required to peel the sky off the stars. Then there's the work of building catalogs, measuring how bright each object is in each band, flagging when it changes, cross-matching positions to other surveys, and attaching the right labels so that later scientists can ask hard questions and get clean answers. All of that takes the romance of a clear night and translates it into rows of numbers that, when read sympathetically, become mountains and rivers again. Beyond the central science, the survey turned up a wealth of neighbors we often ignore. Brown dwarfs, too cool to blaze in visible light, leave solid footprints in the infrared. Embedded clusters still wrapped in natal cocoons appear as knots where there was only smoke before. Extinction maps the measure of how much dust dims and reddens stars along different lines of sight grow finer, which improves everything else that depends on distance. Seeing in the infrared also echoes Gaia's work by improving our 3D picture, where Gaia's parallax and proper motion struggle in the most obscured lanes. Vista can supply the stars that were missing, giving the combined map less bias, fewer holes. Scale has a way of sneaking up on you. To say the survey covered an area equivalent to 8,600 full moons is to imagine a sky quilted edge to edge with pale coins. To say it cataloged roughly 10 times more objects than the 2012 infrared map is to remember how much of the galaxy had been simply hidden from eyes that couldn't look past dust. To add that nearly 80% of the luminous mass has now been probed in the wavelengths that matter for slipping between grains is to picture the curtains finally pulled back in the rooms where most of the family gathers. One of the softer delights of infrared maps is how they de-dramatize what looked chaotic. Star-forming complexes become structures instead of explosions. Filaments lie along magnetic fields. Bubbles carved by earlier generations of stars nest inside one another like rings in a tree. Even the darkest lanes resolve into delicate webs. Follow those webs far enough and you begin to sense how gas flows toward the middle, how bars can channel material inward, how spirals are not only patterns of old stars, but also traffic lanes for the raw material of new ones. Where once the inner galaxy looked like a smear, it now reads like a weather map. Fronts, eddies, clearings, and storms, each with a timescale and a cause. The sheer volume of data might sound like a burden, but it behaves more like a tide pool when the sun is high. Each look reveals something you missed before. A variable star you didn't notice because its phase aligned badly that one night. A faint cluster at the edge of a tile, now bright enough to see because the co-added image is deeper. An alignment of colors that points to a particular chemistry or age. When you hear that hundreds of papers have already emerged and that more will keep arriving, it isn't because facts are being hoarded. It's because the map is rich enough that many different walks can be taken through it without anyone stepping on another's path. There are human touches, too, that make the work feel close. The notion that 500 terabytes is like 3 years of 4K streaming isn't just a cute comparison. It's a way to relate the patience of scientific attention to the patience of ordinary time. The 140 nights of observing spread over 13 years weren't consecutive. They threaded around weather, maintenance, and priorities, just as anyone's long project threads around the rest of life. The camera has its own personality, the mountain its moods, the team its rituals for calibrations and focus checks, and the small superstitions that come with working in places where the stars are almost too many to count. The finds keep bending back to the core goal, making the invisible visible in a way that gives distances and motions, not just pretty pictures. Cepheids serve that goal. So do RR Lyrae, another class of pulsators that can light the early, older populations. So do long-period variables in the bulge that trace the ancient mass distribution. Each class gives a different rung on the distance ladder and a different lens on galactic structure. Together, with color magnitude diagrams built from infrared bands, astronomers can separate foreground from background, bulge from disk, young from old. The result isn't merely a snapshot, it's a narrative with stages, actors, and a set. When you picture the survey footprint, try to feel not only area but intent. The central squares were observed, then observed again, precisely because variability matters. Catching the pulse of a Cepheid requires multiple visits. Catching the drift of a long-period variable requires patience. The extensions added breadth so that structures emerging in one corner could be traced to where they connect. Even without the visual, you can sense the cross-hatching, deep in the middle, wide on the sides, overlap built in. It's a quilter's logic applied to the sky. The claim that this work rewrites how we see the Milky Way might sound grand until you remember how the story looked before. The bulge was a murky glow with guesses nested inside. The dust lanes were walls rather than windows. The inner arms were rumor and inference more than map. Now there are pins and paths. Now there are young Cepheids right where old age was supposed to rule alone. Now there are clusters tucked behind the Triphid and streams glimpsed through holes we didn't know were there. The old picture isn't wrong so much as incomplete. The way a house feels different once you've opened a door that had been painted shut. Stand quietly with that for a moment and let the scale settle. The Milky Way is not a simple pinwheel, but a place with neighborhoods, a bar feeding the center, lanes of new stars bright along arms, a halo of elderly stars and dark matter holding the whole in a soft but insistent grip. Dust weaves through it like weather. Infrared shows you the inside of the weather. When you know where the fog is thickest and where light gets through, you can plan a better walk. You can ask fairer questions. You can build models that match not only the shape, but the timing of what you see. The Triphid's hidden Cepheids, the bulge's young pulses, the long lane of the survey, all of it knits into a calmer confidence about where things are. Distances become less a guess and more a measure. Ages line up in context. Motions make sense when seen against the right background. And there's a tenderness to it too. The idea that we can look across thousands or tens of thousands of light years through soot and crowding and spot a star that is breathing in a rhythm we understand. Once the rhythm is heard, the space between us shrinks into something that can be written down. There's a satisfaction in knowing that much of this will be used and reused as other observatories add their own layers. Radio maps will slide over these, tracing cold hydrogen and the whisper of molecules. X-ray charts will mark the restless remnants of explosions. Mid-infrared surveys will catch the heat of dust itself, rather than the stars behind it. Each is a different register. Together, they make chords. The Vista map gives the baseline that keeps the inner galaxy steady and true. For now, it's enough to let that map glow in your mind like a lantern hung in a window. Think of the thousands of frames, the careful overlaps, the oceans of dust that became translucent, the millions of stars that came forward from behind a curtain as if someone had called their names. Think of the 2 reddened Cepheids peeking past the Trifid and the 35 young pulses near the heart, proof that even the oldest neighborhoods host new songs. Think of the way a survey can be both a technical feat and a lullaby, numbers lining up until they hum. And as the night leans in, remember that none of this rushes. The galaxy turns whether we watch or not. Dust drifts, stars are born and die, waves of density pass along the lanes. Our part is to pay attention long enough, with gentle enough eyes, that the patterns come clear. The first of its kind map is a practice in patience made visible, a way of saying that even in a crowded, cloudy place, seeing through is possible. The hidden becomes a little less hidden. The house feels more familiar. Somewhere behind the quiet and the data, a new corridor has been lit, and we walk it slowly, grateful for the view. Settle into the hush and picture a ribbon of youth threaded through an old, crowded city, a narrow lane of bright windows slipping right across the town square where the oldest stones stand. That is what the team uncovered when they mapped those 35 classical Cepheids, a thin disk of young stars running along the Milky Way's midplane, passing straight through the galactic bulge, hidden until infrared light and patient timing drew its outline. Earlier maps glanced past this lane because dust painted the windows shut and bright. Pulsing stars can saturate detectors, blowing out the very clues we most want to see. When you switch to longer wavelengths and visit often enough to hear the rhythm of each star, the lane comes forward like a footpath at dawn. Its presence and the ages of the Cepheids strung along it, the whisper of steady star formation along the midplane for roughly 100 million years, quiet, continuous, like rain that never quite stops. There may be even younger Cepheids in that same corridor, too luminous for the VVV survey's settings, their crests clipped by saturation. Their absence in the catalog doesn't mean absence in the sky. It means our net, this time, had a mesh size tuned for subtler fish. Imagine them there anyway, fresh, bright, pounding out short periods marking knots where gas compressed recently, where clouds crossed and cooled. The discovery reframes the bulge not as a museum sealed behind velvet ropes, but as a living district where new voices still join the ancient choir. We used to sketch the center as entirely classical, a relic raised in the galaxy's violent youth, its stars old and metal-rich, its structure distinct from the disk. Reality turns out to be kinder, and more complicated. The bulge is not monochrome. Some of its light was born long ago in mergers and collapses. Some of it grows in place, fed by gas funneled in along a bar, nudged by density waves, lit by recent births, stitched into that thin mid-plane disk. Let your attention drift inward, toward the very heart, where the stars crowd thickest, and the night is almost white with their sum. Down there, where dust fences us out in visible light, the infrared survey found something that glows with age rather than heat. RR Lyrae variables, a dozen of them, pulsing a slow, ancient beat in the nuclear region. RR Lyrae are almost the opposite of classical Cepheids. They are low mass, old, metal, poor. Their periods are short, their amplitudes crisp. They have long been our companions in the outer halo and in globular clusters that orbit far from the bright disk. To find them right at the center is like finding the handwriting of the first residents on the wall of the newest train station. It hints that part of the nuclear cluster's backbone was built of globulars that sank inward and dissolved, leaving their elders behind to keep time beside the black hole. Those 12 are few by any practical measure, and strong claims don't belong on small samples. But even a handful can change the flavor of a place. Their presence supports one of the two broad stories astronomers tell about how central bulges grow. In one, the bulge forms early and fast, a byproduct of chaotic mergers of small protogalaxies colliding in a young, hot universe. In that story, old stars dominate, and relics from the globular cluster family end up at the core. In the other, the bulge grows from the inside out, over long seasons, as a bar channels gas inward, and the disk, through secular evolution, raises a boxy, pseudo-bulge from its own material. The truth can host both violent youth and slow adulthood, but these RR Lyrae are good witnesses for the first, pointing to an ancestral contribution from ancient clusters. Think of the center as a tapestry. Some threads were woven under pressure when the loom was new. Others were laid in later by calmer hands. Once you start paying attention to clusters, your eye keeps catching them, especially in infrared. A decade before the bulge's RR Lyrae announcement, two globular clusters stepped out of hiding in the survey's early images. In visible light, a dim smudge called UKS-1 drifted on the right side of a field like a red breath on glass. For a time, it had the title of the faintest known globular cluster played straight. Then you swap in the infrared view, and the background rearranges. A second cluster, fainter still, resolves out of the murk. In the upper left, VVVCL00001. Its stars barely enough to be called a crowd. Soon after, a third new cluster took its place on the list, VVVCL00002. Small and delicate, likely among the closest globulars to the Milky Way's center. Before these finds, the inventory of the galaxy's globulars sat at 158. Adding two in such a dusty, crowded patch felt like noticing two old libraries behind curtains you'd walked past your whole life. Inside the central region, illusions of perspective come easy. One cluster can sit behind another along our line of sight and seem like a companion when it's really a stranger passing by. Even so, astronomers wondered whether VVVCL00001 might be gravitationally bound to UKS-1, a binary globular pair moving through the heart together. We've seen such pairs in other neighborhoods. Centaurus A plays host to tangled cluster systems. The Large Magellanic Cloud carries examples like charms on a bracelet. Bound clusters can share material, exchange stars, and eventually collide. Those collisions, over many orbits, may help build the most massive globulars, the showpieces like Omega Centauri, though some think Omega Cen is the stripped nucleus of a dwarf galaxy rather than a classic cluster grown fat by mergers. Either way, having a potential binary in our own house invites careful watching. Even if future measurements show the pair is a trick of alignment, the question itself sharpens the way we look for bound systems in the glare near the center. Globulars are only part of the harvest. The survey turned up at least 96 new open clusters, looser gatherings with fewer stars, younger by far than globulars, and common as pebbles compared to jewels. Open clusters are born in the disk's nurseries and live fast. The tides of the galaxy and the shoves from passing clouds, pulling them apart over tens or hundreds of millions of years. They don't huddle like globulars. They thin out at the edges and blend into the background, which makes them harder to spot in crowded, dusty fields. Infrared light helps by sharpening the difference between foreground dust and the warmer, reddened stars behind it. One of the finds, VVV CL00003, barely registers as a cluster. When you glance quickly, just a slightly denser sprinkle set against the field. Give your eyes a moment, and a center emerges, a quiet gravity. That one sits about 15,000 light-years beyond the Milky Way's center, on the far side, the first of its class discovered out there. Naming it feels like putting a lighthouse on a coast we rarely sail by. Step back from the individual finds and the scale goes from impressive to intimate. It's not only that more than 1.5 billion objects were cataloged, or that a vast swath of the inner sky was gridded and graced with depth. It's that each discovery changes how the next one will be found. Map the thin disk of young stars through the bulge, and you know where to point for very young variables. Catch RR Lyrae at the core, and you refine searches for ancient signatures elsewhere in the nuclear cluster. Add open clusters along the midplane on the far side, and you trace arm spurs and bar-fed lanes you couldn't follow before. Each set of pins turns a sketch into a route, and routes turn into habits. Soon, the galaxy feels less like a maze and more like a neighborhood walked after dinner. The thin mid-plane disk of Cepheids is a special kind of compass. Cepheids come with built-in rulers. The period luminosity relation transforms their pulse into distance, and with their colors, age. They also huddle where star formation is recent and gas remains thick, which means their positions trace the skeleton of the places where the Milky Way is quietly still building itself. That the disk runs right through the bulge tells you gas has a way to reach the center. Bars can coax it inward. Density waves can carry it. Interactions can stir it loose from its old orbits, and that the dust lanes we see aboard visible images are not walls so much as drapes. In infrared, they flutter, and behind them, the corridor is busy. The ages under 100 million years, some near 25, prove the activity isn't a fluke. It has persisted through the last stretch of galactic time the way a spring creeps along a hillside, finding new outlets and pooling quietly wherever the slope allows. Set those young pulses beside the older RR Lyrae, and you get a time slice of the center that is almost cinematic. One population beating fast with youth, the other steady with age, both sharing the same cramped streets. It suggests that the nuclear region has grown both by accretion of ancient systems and by fresh star birth, the way an old town adds a market by repurposing a square while also absorbing villages at the edges. Infrared surveys finally give us the city plan, rather than a night skyline seen through fog. Globular clusters themselves carry long memories, Their stars formed together when the universe was smaller and colder. They preserve chemical signatures of their first gas and the faint traces of subsequent enrichment. Their distribution around a galaxy can tell you about its assembly, how many dwarfs merged, when streams were captured, how the halo grew. Finding new globulars in the most obscured parts of the sky is like discovering family albums in a cellar. The stories inside rewrite parts of the family history. VVVCL00002, if it is indeed among the closest globulars to the core, can help pin down the dynamics of the inner halo and the transition to the nuclear cluster. Its orbit, once measured, will tell whether it is skimming the bar, diving through the plane, or circling in a more tempered path. Each scenario leaves different signatures in the motions of the stars around it. Open clusters, by contrast, teach us about the present tense. Their ages, often a few tens of millions of years, line up well with the timescales of spiral arm crossings and bar-driven inflows. Their chemicals carry the recent enrichment from supernovae and winds. By placing them in 3 dimensions across the bulge and disk, the survey draws a contour map of where gas still has the right conditions to collapse. That map complements the thin Cepheid disk and fills in the picture of continual star formation along the midplane. Where open clusters appear, you can bet the gas density has been high and the turbulence gentle enough to knead clouds into stars without tearing them apart. It helps, as you listen, to remember how much this depends on light you cannot see with your eyes. Infrared, at these wavelengths, is a way of feeling warmth through cloth. Dust that would block visible light often emits or transmits in the near IR. It becomes less a barrier and more a context. Tucked inside the details are small technical graces, how the 4.1-meter mirror gathers just enough of the dimmest stars without washing out the bright ones, how detectors cope with the higher background that infrared skies bring, how repeated visits, spaced out over months and years, let astronomers subtract the sky from the stars cleanly and stitch overlapping tiles without seams. There is art in how you choose exposure times so that faint clusters can be coaxed into view, while the brightest Cepheids don't blow the tops off their waves, and craft in how you salvage saturated objects by looking at wings of the point spread function or by cross-matching with other surveys that caught them unsaturated on quieter nights. None of this happens in a vacuum. The Vista maps breathe easily when laid beside Gaia's parallax-rich catalog. Where Gaia's visible light vision falters in the dustiest lanes, Vista supplies the missing bodies. Where Vista's view fixes positions and colors through the fog, Gaia's motions give orbits and velocities. Together they make a truer 3D atlas of the inner Milky Way than either could alone. Pair them with radio maps of neutral hydrogen, millimeter wave surveys of cold molecular clouds, and X-ray charts of hot remnants, and the bulge goes from mystery to mechanism. You can trace where gas is, where it's going, what forces are shaping it, and which populations record those forces in their ages and motions. It's easy to say, rewriting our understanding, and mean nothing but enthusiasm. Here, it's literal. Before this work, the far side of the galaxy's midplane was a dim rumor. Open clusters were counted mostly on our side. Globulars near the center were poorly catalogued. The presence of young classical Cepheids in the nuclear region was not expected. Now we can follow a thin thread of youth right through the bulge. We can point to our Lyrae among the central throng and argue for an ancient contribution. We can pencil in new clusters where the map had only smudges. Each change tightens models, bar length and angle, pattern speeds for density waves, the degree to which the bulges box, peanut versus classical, how gas flows shape where the next stars will ignite. On quiet nights, the numbers take on a softer meaning. The thought that only 158 globular clusters were known in our galaxy not long ago, and that infrared eyes added 2 more in one dusty window, feels like an invitation to keep looking. The idea that at least 96 open clusters were hiding behind the curtains along the midplane tells you how much the visible sky had kept off the books. The ages 25 million, 50, 100 sound like days compared to the elders 10 billion. And yet, in those days, the galaxy writes the headlines that light up the arms and shape the photographs we recognize. Sometimes, drifting along this story, you might picture how these clusters live and die. Open clusters dissolve into the field, their families scattering across the disk until only a faint chemical kinship hints that they were born together. Globulars hold tight, surviving tides and passages through the plane, leaving behind tidal tails and streams that can be traced like chalk lines to reconstruct their paths. If 2 globulars are bound, they orbit one another for a while, trading stars across a faint bridge until a close pass heats them or tides tear them toward union. In a few rare cases, the union builds something bigger. In others, it leaves an elongated, wounded survivor. The nuclear region can swallow whole clusters, heating them, shredding them, and mixing their elders into the central swarm where RR Lyrae now beat their quiet drums. The thin midplane disk of classical Cepheids has its own fate. It will persist as long as gas continues to flow inward and conditions remain right for massive star formation. If the bar strengthens or weakens, if the pattern speed changes, if nearby interactions tweak the inflow, the lane may shift or split. Even in 100 million years, just a few turns of the inner disk, the pattern may look different to watchers then. For now, it is enough to know that our old galaxy carries a young artery through its chest, warm and bright, and that our maps can finally see it pulse. Let your mind walk once more from the far side open cluster VVVCL 00003 back through the bulges veil to the central cluster of RR Lyrae. Each step is a change in age and chemistry, in crowding and confusion, in what light can help you. The infrared survey laid stepping stones across that river. When paired with Gaia's rhythm of motion and other wavelength signatures, it makes a crossing you can manage without getting lost. The discoveries do not end with these. They are beginnings that point at other corners to search. Where the thin disk meets the bar, more young variables should be found. Where globular orbits plunge through the plane, streams should fan out. Where open clusters sit in strings, you might be seeing the handiwork of a spiral arm spur or an elbow of gas thrown off by the bar. It is tempting to demand a final picture, a settled answer to what the bulge is and how it came to be. The sky refuses that kind of closure. It offers evidence layered in time, an ancient rhythm from RR Lyrae, a fresh flash from Cepheids, a dim cluster blinking on in the infrared only because the right night was chosen and the right filter used. The right posture is patient curiosity, with the vista maps as foundation stones. Sharper instruments will build higher walls of detail and cut clearer windows into the dust. Resolution will sharpen, sensitivity will deepen, the number of known clusters will rise, the catalog of variables will lengthen into the millions. Each new rung on the ladder will be tested against the old. Does the thin disk persist? Do we find saturated youngsters by watching with different eyes? Are any of have the candidate binaries truly bound? How many clusters has the center swallowed? And can we reconstruct their family trees from the stars that remember? Let the night keep its quiet while you imagine the answers drifting closer. The team's thin disk, the bulge's ancient pulses, the hidden pairs in open gatherings, the sheer headcount of stars pulled from behind the curtains together. They make the inner Milky Way feel less like a rumor and more like a place you could stroll, one block at a time, with the lamplight steady and the air warm. Different wavelengths are just different kinds of lanterns. Infrared makes a room of what used to be a wall. Visible light shows the faces that smile back when the dust is thin. Radio tells you where the pantry is full. X-rays outline the fireplaces where old wood still glows. When you carry all those lanterns together, you don't banish the mystery. You honor it by seeing more of its edges, by knowing which shadows are empty and which are doorways. Somewhere in the middle of this is a quieter truth that helps sleep come easy. Our galaxy is not a fixed diagram. It is a living thing with habits and surprises, a place where elders and newborns share the same streets, where ancient clusters leave fossils in the heart and new stars trace a thin, bright path through the dust. We misunderstood parts of it for so long, not because we were careless, but because we lacked the right light and the right patience. Now that we have both, the map opens like a hand, and we move through it slowly, grateful, letting the scale and the softness of it lull the mind, while the facts keep their gentle, trustworthy beat. Let your gaze rest on a deep image from the James Webb Space Telescope, the kind that feels like holding a seashell to your ear and hearing the oldest murmurs of light. Close in, the nearby stars of our own Milky Way shine like careful pinpricks, each one splayed with delicate diffraction spikes, snowflake shapes drawn by the telescope's mirrors. Far behind them, quieter and older, whole galaxies unfurl as pale smudges, some round and serene, some spiraled like slow whirlpools, each a city of hundreds of billions of suns softened by distance into a single brushstroke. In most of those faraway cities, you won't pick out individual residents. Their lights blend into a faint, collective glow, a choir heard from across a wide valley. Yet there is one kind of voice that cuts through the crowd. Sometimes, at the center of a distant smear, a single point burns with such ferocity that it outshines the rest of the galaxy combined. A lighthouse in the fog, a quasar. Here's the part that tilts the mind. Tiny kin of those beacons seem to live among us. Not in the sense of a second sun blazing at noon, but as smaller, quieter analogs tucked inside the Milky Way microquasars, close enough to study without threatening the calm of our nights. It sounds like a contradiction. How can something born of extremes be hiding in a sky we thought we knew? The answer arrives when you think about sight as a set of senses rather than a single one, about the way different wavelengths of light reveal different rooms in the same house, and about how motion and time can turn a blinding flare into a readable story. For centuries, we looked up with eyes tuned to the same narrow rainbow we used to read and walk visible light. In the mid-1900s, astronomers built new ears for the sky and began surveying it in radio waves, longer, cooler ripples, the night vision goggles of the cosmos. At first, radio maps simply redrew what we already knew. Spiral galaxies sang in radio as they did in visible. Supernova remnants whispered in arcs and loops. Then, something unfamiliar appeared in the weave bright radio sources with no obvious counterpart in visible light, speckled across the sky like embers with no hearth. By 1960, there were hundreds, The possibilities ranged from the sober to the playful. Alien transmitters are romantic. Nature, it turned out, had cooked up something stranger and more instructive. With sharper optics, those radio beacons revealed pinpoints in visible light, as well quasi-stellar radio sources. Star-like, but not a star. Quasars. Too compact to be ordinary galaxies, too radio-loud to be ordinary stars. The decades that followed were a long exhale of figuring out what engine could possibly make such a thing. The answer: gravity's deepest well, wrapped in a whirlpool of matter. At the heart of many large galaxies sits a supermassive black hole, millions to billions of times the sun's mass. When gas and dust fall toward it, they don't dive straight in. They spread into an accretion disk, a flat ring of material orbiting so fast that rubbing and shearing heat it white hot. That stored gravitational energy becomes light visible, ultraviolet, X-ray, pouring out from the disk's surface. In some systems, magnetic fields thread the disk and the black holes spin, collimating a fraction of the inflowing matter into narrow, relativistic jets that spear outward, above and below the disk, at near light speed. Those jets stir intergalactic space, and their charged particles hum in radio as they dance through magnetic fields. Put all that together, and a single engine can outshine an entire galactic population of stars. Our own center holds a black hole too, Sagittarius A*, a quiet, compact heavyweight. Its table is presently tidy. Little gas swirls within reach, so the accretion glow is dim, and the jets, if they exist at all, are shy. If the Milky Way were mid-merger, its pantry shaken open by tidal forces, Scar A times might flare into quasar territory. From a distance, such drama makes for a spectacular picture. Up close, it's a hazard. Quasars bathe their neighborhoods in high-energy radiation, a rough climate for biology. In a way, our calm core is a kindness. The sky remains dark enough for us to sleep. The oceans keep their chemistry. The biosphere hums. Yet the universe rarely frames choices as either-or. In the spaces between extremes, lie versions small enough to study and bright enough to teach. Stellar mass, black holes, remnants of massive stars that collapsed at the end of their lives, speckle galaxies by the many. Most wander quietly, but some live in binaries, paired with a companion star. When that companion swells or its orbit decays, gas can stream toward the black hole and settle into a miniature accretion disk. Scaled-down physics, familiar shapes. If conditions line up, small, steady jets launch. These are micro-quasars, not city-leveling searchlights, but bright lanterns, close, detailed, safe time-lapse versions of the bigger drama. One of the most storied is SS-433, logged in the late 1970 seconds, and instantly promoted from a mere catalog entry to an object of fascination. The name hides a complicated duet, a Type A supergiant star, and a stellar mass black hole orbiting their shared center of mass. Gas from the supergiant feeds the black hole's disk. The disk responds by flinging out twin jets. Our line of sight slices the system edge-on, so the jets stream perpendicular to our view, never aimed at us, fortunate for detectors and daydreams alike. Still, their light spreads in many directions, and we can catch it in radio, optical, X-ray, gamma ray, each wavelength telling a slightly different truth about temperature, speed, and composition. Listen carefully, and the jets reveal layers. Close to the black hole, inner jets extend a couple of light years, brief, fierce streamers that fade quickly. Farther out, at a remove of roughly 75 light years, outer jets appear great ghostly structures stretching an additional 300 light years before dissolving into the ambient medium. Why do they turn on again so far away? Why do they stop where they do? The answers are still assembling themselves. Some of the scaffolding came into focus when a collaboration using the HES Observatory, an array designed to catch the flickers of the most energetic gamma rays, mapped where the system shines hardest. Gamma rays are the top notes of the spectrum, photons with energies high enough to be measured in billions and trillions of electron volts. Ordinary starlight is soft by comparison. You don't get gamma rays from a warm surface. You get them from processes that hurl particles to extreme energies and let them trade that energy to light. In SS-433's outer jets, gamma rays show up abundantly. More intriguing, the distribution of their energies maps onto location. The hottest photons, carrying more than 10 tera-electron volts, each about 10 trillion times the energy of visible light, cluster near the inner base of the outer jets. As you move outward along the jets, the gamma rays trend to lower energies. That gradient reads like a diary of losses. If gamma rays are born when very fast electrons smack into lower energy photons and boost them, an exchange called inverse Compton scattering, then the farther you go from the base, the more those electrons have already spent themselves colliding, the less energy they have left to gift to passing light. The HESS team found exactly this pattern. When you turn the knob from observation to inference, you get a picture in which electrons start extraordinarily energized and gradually cool as they scatter light. It's a simple story, made believable by numbers. The right photons in the right places, carrying the right amounts of energy. The puzzle then tilts. Where did the electrons get that much energy in the first place? Models of the launch region suggest that material in the inner system leaves at a quarter of light speed. Not shabby, but not enough. By the time those electrons are busy in the outer jets, their effective speeds appear to press against the cosmic limit, greater than 99% of light speed, implying energies multiplied by factors of a billion compared to their start. Something along the way is acting as an accelerator, and it has to be both patient and efficient. One elegant mechanism wears the name diffusive shock acceleration. Picture a shock front, a thin boundary where conditions jump, like the edge of a supersonic wave. Magnetic fields tangle around it. Charged particles wander in those fields, bouncing randomly back and forth across the shock. Each crossing can add a small increment of energy. Most particles drift away before they get rich. A few, by chance, zigzag many times and come out extraordinarily energized, like a leaf caught and recaught by gusts until it clears the roofline. At the base of SS-433's outer jets, a standing shock born of the jet slamming into a denser region or colliding with an earlier outflow may be handing out these boosts. It doesn't need to be perfect. It needs to be persistent, and the statistics do the rest. With enough tries, enough electrons climb to hundreds of tera-electron volts, the range needed to seed the gamma rays HESS detects. The beauty of a nearby microquasar is partly in proximity and partly in pacing. Everything is smaller and quicker than in a supermassive system. Structures that would take centuries to evolve around a galaxy-scale black hole can change over years in a stellar-scale one. That time-lapse effect turns the unwatchable into the watchable. Jets precess, knots brighten and fade, shocks grow and weaken. With radio arrays and X-ray telescopes, with instruments sensitive to gamma rays and to the subtle glow of infrared synchrotron light, you can follow cause and effect rather than reconstruct it from fossil traces alone. In the quiet of a late hour, that feels like having front row seats to a physics play. No narration needed, just the actors and their lines of light. These small beacons carry lessons that scale. In the heart of a distant quasar, magnetic fields and plasma flows must also negotiate. Shocks must also accelerate. Electrons must also choose between radiating away energy or giving it to photons via scattering. The proportions differ, the rhythms differ, the wallpaper changes, but the choreography rhymes. By reading the clean, close script of a microquasar, we gain grammar we can apply to the muddier, grander texts at cosmological distances. We learn how jets collimate, how they maintain coherence over vast lengths, how and where they deposit their energy, how they light up surrounding gas into lobes and bubbles that redraw the circumgalactic medium. Back at the start of this thought, you were holding a web image in your mind nearby spiky stars and faraway clouded cities. Now add a layer of imagination. In some of those distant galaxies, hidden cores blaze as quasars, their light stretched and softened by space. In our own galaxy, tucked into neighborhoods of gas and dust, smaller cousins hum. The physics is kin, the stakes gentler. A supergiant star feeds a compact companion. A disk forms, hot and thin as a blade. Jets find their rails. In the inner region, they fade after a couple of light years. Farther out, 75 light years from the source, outer jets take up the relay and run for 300 more. As if the system breathes twice. A quick inhale, a longer, deeper exhale. It's natural to want clean boundaries, a crisp map with labels. The sky asks for a softer posture. We used to speak of quasars as rare and exotic. Now, we understand they are a phase, intense, episodic, of many galaxies' lives. We used to imagine our center as fixed in a single mood. Now, we know it too has weather, and that the right inflow could change its temperament. We once thought gamma rays belonged only to the most violent explosions. Now we see they also weave through steady processes when magnetic fields and shocks work together over time. None of this blurs the awe. It makes the awe legible. The history that brought us here is its own lullaby. Radio astronomers mapped the sky and found new sparks. Optical observers chased them down and gave them names. Theorists scribbled, and then X-ray and gamma-ray telescopes tested the scribbles. A catalog entry, SS-433, became a system with a personality. What began as points became pairs. What began as guesses became measurements. Two jet regimes, inner and outer. Gamma rays above 10 tera electron volts concentrated at the base. Lower energy gamma rays stretched farther downstream. Electrons accelerated from about 0, 25 C, to beyond 0, 99 C, through diffusive shock acceleration, a geometry that keeps the jets off our line of sight while still flooding the surrounding space with signposts we can read. The details are crisp. The feeling remains soft. It's the hush of watching something very far away and very fast unfold without haste in your mind. And when you return to that web image one last time, notice how the foreground stars spiky, local frame the distant swirls without upstaging them. Our galaxy is like that in the larger story, quiet at the core, for now, but not empty of drama. Microquasars flicker along the arms and through the bulge, too small to dominate, bright enough to teach. Their jets sketch invisible highways, their gamma rays write marginalia in the spectrum, their orbits and disks and shocks hum the same song as their grander cousins, at a gentler volume. It's comforting to know that the universe offers both extremes and study guides. Let that comfort settle. The cosmos is not a single blaring trumpet, but a layered ensemble. Visible light gives you the melody. Radio adds the low, steady drone of charged particles looping through fields. Infrared warms the hidden rooms where dust has drawn the curtains. X-rays and gamma rays sprinkle in the bright percussive accents of acceleration and shock. Microquasars are little percussionists, keeping time close to home, letting us hear clearly what distant quasars perform in huge halls with echoes. If you listen long enough, if you give your eyes time to adjust to the dim and the bright, the pattern resolves. The lighthouses in the fog stop being mysteries and turn, sweetly, into landmarks guides for a gentle walk through the night. Settle a little deeper and picture gravity as a well so steep that even light, swift and nimble as it is, cannot climb back out. Black holes are the densest rooms the universe knows how to build, places where matter has been pressed until space itself folds inward. It makes a gentle kind of sense to find the largest of them in the busiest parts of town, down in the hearts of galaxies, where gas and dust have drifted inward for billions of years, where stars are born, live, and die, and their ashes keep sliding toward the center like snowmelt, finding a river. Feed a fire long enough, and it becomes a furnace. Feed a black hole long enough, and it becomes supermassive, wearing masses counted in millions or billions of suns. Here is the mind-tilting part. Some of the heaviest black holes we've met look young. Peer far out, and you're peering back in time. Light takes its time, crossing a growing universe, so a galaxy 10 or 11 billion light-years away is seen as it was when the cosmos was young. Those distant beacons often host Leviathan black holes already swollen with mass. If the universe is about 13.8 billion years old, and we catch a quasar whose light left when the universe was barely a few billion years into its story, then the engine we're seeing had only that much time to grow. How did it bulk up so fast, while our nearer, older centers look comparatively small and quiet? Numbers can be soothing when they're held gently. The current record holder most people whisper about is TON 618, a quasar whose central black hole is estimated around 66 billion solar masses, so heavy that all by itself, it rivals the total mass and stars of a big galaxy. The light we see from TON 618 set out roughly 10.8 billion years ago, which means we're viewing it as it was then, a youth by cosmic standards, perhaps no more than about 2.8 billion years old at the time that light began its journey to us. Put that beside the center of our own home. Sagittarius A*, the Milky Way's central black hole, weighs in at about 4 million suns. Andromeda's central engine is bigger. Call it a couple 100 million suns, but still tiny compared to the great ancient quasars. The contrast feels like finding a sapling where you expected a sequoia and, far away on the horizon, a giant that must have grown overnight. Part of the answer lives in how we're able to see. Black holes themselves don't shine. They erase. We infer them by their company, the way stars orbit a dark mass, the way gas heats as it falls, the way jets thread the sky. Our instruments tuned to this work are young, Only in the past few decades have we gained the clarity to weigh a central object by watching nearby stars loop in tight ellipses, or to measure gas swirling at high speeds a few light hours from a horizon. Even the images you've seen of M 87 times and Sagittarius A times, those soft donuts, ember glow rings, are the result of a worldwide interferometer stitching data together with a patience that feels like a mantra. This is careful, difficult work. It means our census nearby is incomplete, and our sense of typical is colored by what we can catch. Farther out, the bright ones speak first. Quasars are black hole engines in a specific mood. When the pantry is full and gas pours inward, matter doesn't fall straight in. It settles into an accretion disk, a hot, thin whirlpool where friction heats the gas until it shines across the spectrum. Magnetic fields thread the disk and, in some cases, shepherd a fraction of that flow into narrow, relativistic jets. The glow can be astonishing. A single quasar can outshine all the starlight in its host, which is why, when they were first cataloged, they masqueraded as stars, small points, impossibly bright. Ton 618 blazes with the combined light of roughly 140 trillion suns. At that brightness, its galaxy fades into the glare. Only the lighthouse is obvious. Brightness has its own bias. When you look far, you're sifting for the loudest voices. Malmquist bias is the soft name for a simple effect. At large distances, you mostly detect the bright things, so the population you think you're seeing is tilted. It doesn't mean the universe only put monsters far away. It means the monsters stand out from farther off, while quieter cores and unassuming black holes go invisible at those ranges. A massive central black hole without a feast to fuel a quasar can sit in a distant galaxy and remain anonymous. Its host is too dim to register against the background. Up close, we can weigh modest black holes by the dance of their companions. Far away, we learn the names of the loud. The rest of the answer belongs to time's early weather. In the young universe, matter was closer together. Gas hadn't yet been locked into as many long-lived stars. Galaxies were merging more often. Their halos were fat with cold material. The cosmic pantry was stocked. Under those conditions, central black holes could gorge sometimes in near-continuous flows, sometimes in feasts triggered by mergers that funneled gas straight to the core. The stream was strong enough that the accretion could be Eddington limited, balanced by the push of outgoing radiation, or even, at times, briefly above that limit, in messy, clumpy flows. Growth under those rules can be fast. There's a time scale, the salpeter time, that tells you how quickly a black hole can grow when fed efficiently, tens of millions of years, for its mass to double if conditions remain generous. Stack enough doubling times in a few 100 million years and an initial seed can become a giant. Seeds themselves might have come in two sizes. Some black holes began as stellar leftovers, cores of massive stars that collapsed, a few to a few tens of solar masses. Others may have been direct collapse seeds, formed when gargantuan pristine gas clouds in the early universe failed to break into normal stars and instead fell inward, wholesale, skipping the small-scale step and leaving behind black holes of 100,000 suns or more. Start larger, and the climb to billions becomes easier. Stir in galaxy-galaxy mergers, which not only feed the center but also bring in their own central black holes to coalesce, and you have a recipe for rapid growth while the universe was still stretching its arms. Closer to home, the pantry runs leaner. As epochs passed, gas turned into stars. Supernovae and stellar winds heated what remained. Some of that gas was blown out into halos or into intergalactic space. Some sank slowly. Some became planets and calm, long-lived suns that sip their fuel and do not return it quickly. Feed rates dropped. Bars and spiral arms can still shepherd gas inward. Close encounters can still upset a disk, but the grand feasts are rarer. Many central black holes slid into a quiet, routine, low accretion, low light. Our own Sagittarius A times flickers, but mostly dozes. If a big cloud falls in, it stirs, then it settles again. The physics at the heart of a quasar is wild and exquisite. In an accretion disk, matter orbits fast enough that neighboring rings rub. That friction turns orbital energy into heat. Hot gas glows. The inner regions glow hardest. Magnetic fields, twisted by the disk's rotation and anchored in plasma, can launch jets along the poles, narrow and clean. The whole engine is a conversion machine, turning gravitational potential into light and motion with an efficiency that rivals and sometimes exceeds the nuclear furnaces inside stars. That's why a disk can pour out thousands of times more light than all its galaxy stars combined. It's difficult to hold the scale in your head. It's easier to imagine warmth at the mouth of a cave, a wind that smells of lightning, and to remember that such things can be both beautiful and harsh. Even as we rest in these images, it helps to keep an eye on the ways we measure. The Event Horizon Telescope, dozens of dishes acting in concert, needed exquisite synchronization to see a silhouette against glowing gas. Each image is a long meditation, pieced together from nights of good weather stretched across the planet, from algorithms that knit radio waves into a picture of something smaller in the sky than a grapefruit on the moon. We can't yet do that for dozens of targets. We read most black holes from farther away, the speed of gas in broad emission lines, the flicker of light as a disk breathes, the orbits of stars around a dark center, the jet whispers in radio. Each method has a reach. Each has a bias. Taken together, they paint a truer portrait than any single glance. When you stack these pieces, the paradox softens. The biggest black holes we see far away look young because we're meeting them early in the universe's morning, when the pantry was full and the roads to the center were crowded and quick. We don't see many equally big ones nearby because our local giants, if they ever reached such sizes, are quieter now, their fuel trickling rather than pouring. Because very massive but quiescent centers are hard to weigh at distance, and because our own corner might simply never have played host to the wildest early feasts. Add Malmquist bias to the mix, bright things found first, faint things missed at range, and you have a recipe for an apparent tilt that is partly true and partly a trick of the light. There's another quiet rhythm worth holding. The universe shifts its energy with time. Quasars rose in number when the cosmos was a few billion years old and have faded in prominence since, a trend people sometimes nickname cosmic downsizing. Big engines burned early, smaller ones hum longer. It isn't a moral, just a note about supply and demand, how much gas is cold, how much is clumpy, how deep the potential wells are, how often galaxies collide. Over time, gas turns into stars. Some stars die into neutron stars or black holes and lock their mass away. What remains mobile becomes rarer. In some stories about the far future, this trend runs to its quiet end. People call it the Big Freeze. Stars wink out over unimaginable spans. Matter collapses into remnants. The last sparks are faint and far between. The night grows gentle and cold. For now, the night around us is anything but empty. Even a small central black hole reshapes its neighborhood. Even a low luminosity accretion flow can put out a soft X-ray glow. Even a dozing giant can wake when a cloud wanders too close. Tidal streams remind us that galaxies still merge. Long filaments of cold gas thread the dark like rivers under snow. Bars and spirals keep nudging material inward. We are lucky, in a quiet way, that our central furnace is modest. A quasar in our living room would write a different climate across Earth, a harsher light and a thinner margin for life. Learning from distant giants, we can be grateful for local lullabies. If you hold Ton 618 inches, your mind, its mass, like a mountain range, its light, a second artificial dawn in a far-off sky. Let it be a symbol not just of enormity, but of timing. Conditions make possibilities. Early on, the universe built many massive engines because it had the ingredients arranged in a generous way. Later, those ingredients spread out, cooled, and settled. Nearby, we have the tools to measure modest engines with grace. Far away, we glimpse the titans that call to us because they are so bright that distance cannot drown them. Both truths sit together without quarrel. And if the thought of distant brightness still nags at you, ease it with one last image. Imagine the universe as a vast field at dusk. In the distance, where the air is thicker with mist, where the hills are closer together, you see bonfires, high and ravenous, burning young wood that's been stacked in a hurry. Nearer to where you stand, the fires are smaller. People are adding logs one by one, careful and slow. Some fires have gone to coals. Some are waiting for more wood. A few flare and settle, flare and settle, in a rhythm that promises warmth without drama. None of this is unfair. It is simply a matter of where the wood is, how quickly it's gathered, and who lights the match. Let your eyes rest on a deep field where the night is crowded with time. In one corner, a soft curve of light has been stretched into a thin arc. In another, little commas and crescents echo around a heavy, pale center. We're seeing light that left when the universe was only about 750 million years old, barely out of its first breath. So each smudge is not just a dot, but a memory. Count the smudges and you run out of fingers quickly. In a field like this, there are on the order of 10,000 galaxies, a small town by cosmic standards, and still vast enough to quiet the mind. The image wears distance like perfume, very old, very faint, and yet some of the details sharpen because nature helps us look. Between us and that early light sits a cluster of galaxies, a heavy knot in the web, and heavy things bend the path of passing beams. Gravity doesn't pull on light like a hand tugging a sleeve. It curves the stage itself. Space-time dips around mass, and light, which always walks the straightest line available, finds its straightest line now follows the bend. When the geometry lines up source, lens, and us in a neat chain, the arc of light can grow into a ring, an Einstein ring, or turn into a handful of repeated images splayed like petals around the lens. Sometimes you see the arcs without noticing the lensing galaxy at first. Then your gaze finds the big, smooth ellipticals at the cluster's center, and the pattern clicks. In the heart of one such field stands Abell 1703, about 3 billion light-years away, its mass crumpling space-time, just enough to give us a magnified glimpse of what lies behind. It's a natural magnifying glass with fingerprints of relativity on the rim. There's something lingeringly elegant about the way different kinds of galaxies carry themselves. Some ellipticals look flawless from a distance, no patchy dust lanes to interrupt the glow, no ragged arms, just an even wash of old starlight, as if time had polished them. Some spirals are grand and patient, their arms wrapping with a satisfying symmetry around a bright core like ribbons, wound carefully on a spool. And then there are the ones that refuse to sit still in a tidy category, the peculiar shapes gathered into an atlas by a curious mind. The ARP catalog of peculiar galaxies is a little museum of misbehavior, bridges and tails, rings and hooks, shells and knots, each a freeze frame from a long, chaotic dance. They are not messes, they're stories caught mid-sentence. At first glance, the galaxy called M60 plays the conservative part. It sits about 57 million light-years away, a massive elliptical with a smooth face that suggests it has long since spent most of its cool gas, leaving little raw material for fresh blue stars. Near its center lurks a notably heavy black hole, weighing in at roughly 4.5 billion suns. Impressive, yes, but the overall portrait is serene. A small pan-out, and the tranquility gets interesting. Right next door in projection lies a spiral, NGC 4647, stitches of dust and hints of arms, making a contrast so striking you can't help expecting fireworks where they meet. And yet, no obvious tidal tails, no warped disks, no fans of stripped stars. The oddness is the lack of obvious oddness. That's because the closeness is a trick of our sightline. One sits in front of the other, not shoulder to shoulder. The chasm of depth steals their chance to pull at one another's hems. A smaller surprise hides in the corner, easy to overlook until someone points. The tiny blur goes by the name M60UCD1, and it is a galaxy in the technical sense, while being barely a city block by galactic standards, about 300 light-years across, and holding something like 200 million solar masses. Ultra-compact dwarfs wear their stars like tight sequins. Near the center, the density becomes startling. Stars packed about 15,000 times more thickly than in our neighborhood of the Milky Way. Imagine the night sky there, no night at all, perhaps just a constant silver. In X-rays, a point of heat glows at its heart, a sign that a black hole is likely there, and estimates put it near 10 million solar masses. For such a small system, that's enormous. A hint that M60UCD1 could be the stripped core of a once larger galaxy, its outer layers tidally peeled away long ago by a bigger neighbor, the leftover nucleus walking on as a tight, bright knot. Galaxies can shed like that. They can leave ghosts of former selves for us to find. Now and then, the dance is not subtle. Two galaxies can meet in a way that rings the whole structure like a bell. At about 440 million light-years, a peculiar pair shows what happens when a spiral gets struck in the face by an intruder. The result is a ring galaxy, a bright blue hoop, sparkling with newborn clusters. The head-on hit sends a density wave rippling outward through the disk, compressing gas as it goes. The compressed gas lights up with star formation, turning the ring into a necklace of hot, young stars that outshine the older population beneath. The timeline we read in the colors is gentle and tragic. The most massive of those newborns live in a hurry. Their lifespans count in tens of millions of years. If the main starburst peaked 15 million years ago, Many of those giants have already blown themselves to pieces as supernovae, leaving behind neutron stars and black holes, stirring the gas, carving bubbles. The reddish chunk off to one side could be the galaxy's old nucleus, off-center now, riding inside its own wake. The partner in the collision, an elliptical, shows less drama. Without a rich supply of cold gas, its main response to tidal forces is to shiver and ruffle, not blossom. There are gentler peculiarities that demand a longer gaze. NGC 1097 sits at a distance that makes it a steady favorite. From afar, the face looks like an eye, the core a pupil, the encircling star-forming ring an iris stitched with bright knots. Each knot is a hot bubble in hydrogen where stars are germinating. Zoom in to other wavelengths, and you can watch dust joining the inward flow along subtle lanes, little streams that feed the central black hole. The center is not only an eater, it is a gardener of sorts, cycling gas in and out as star formation and inflow compete. Then, zoom all the way out, and you find something that doesn't quite fit the vocabulary of arms or rings. For faint, straight-ish features offset in an X around the core. They look like jets but don't glow in hydrogen the way gas-rich streams should. Instead, they appear starry, ancient, low on gas, leading to the reading that they are the stellar bones of a cannibalized dwarf or two. The fossil trails left by galaxies the larger host has already consumed. A companion, NGC 1097A, a small elliptical, orbits nearby like a moon, a reminder that most disks do not live alone. Sometimes the sky gets playful with shapes. Two galaxies seen mid-encounter arrange themselves into something that looks like a bird leaning over an egg. The bird, once an ordinary spiral, wears a long, tidal streamer torn off by the passing elliptical. The egg sits nearly unruffled, its smooth light only slightly skewed into an oval. Along the edges of the distorted spiral, blue patches mark starburst triggered by a passing tug. Dust lanes stand out when the light hits at an angle. In some 3D reconstructions, those lanes look like they're lifting, detaching, becoming filaments that will either melt back into the disk or rain down later, as fountains do after they rise. The distance, roughly 350 million light years, makes the scene safely remote and intimately legible at the same time, like a weather map of a storm already passed on. Not every galaxy wears its drama on the outside. One, no bigger than the Large Magellanic Cloud, lives as a single, persisting shout. NGC 1569 is a dwarf starburst tucked near the Maffei group, compact, about 6,000 light-years across, and close enough at roughly 11 million light-years that we can pick out its components clearly. Gas and dust here have been squeezed by the company of larger neighbors, and the compression has tipped it into a rapid bloom star formation, occurring at rates 100 times those in our more sedate Milky Way. At the center, two superstar clusters shine, tight gatherings of massive, young stars, whose winds and supernovae have blown red material outward, hollowing caverns and inflating shells. The halo's small white points are older residents, quieter, watching the fireworks from a little remove. In a place this small, feedback the pushback from young, hot stars can rearrange the whole structure, stirring gas out to the edges or even into intergalactic space. A dwarf, in a loud mood, can change its life in a single breath. Hold that sense of scale while looking at one last stage, a theater where many actors share a single frame. Three galaxies approach one another along the threads of the Hercules supercluster, about 500 million light-years away, and we're catching them at the moment before impact, close enough that soon feels like a word we can use without irony, even though cosmic soon can mean tens of millions of years. A third companion hovers above the pair, likely bound to their fate. That this happens in a supercluster is not a surprise. Matter flows along filaments the way water follows stream beds. The large-scale map of the universe looks like a web. When you color in the parts, we can see galaxies collecting along long, narrow strands where gravity has funneled them, leaving vast, quieter spaces between. In one of those quiet spaces sits the Boetes void, famous for feeling like a note held between chords, immense, underpopulated, a reminder that emptiness is as much a part of the pattern as brightness. When you see the three on the road to a merger, remember that their future will print itself not just in tides and tails, but in the way their central black holes spiral together, launch waves of gravity, and alter the climates of their new, shared home. As the mind drifts across these scenes, the neat arcs of lensing, the polished calm of ellipticals, the confident sweep of spirals, the rebellious grace of peculiars, it's tempting to file each into a drawer and close it. But the night asks for a looser filing system. What we call types are often phases. A collision can turn a spiral's ordered lanes into a ring of blue fire. A quiet elliptical can wear shells for a while, echoes of a meal it has just finished. A dwarf can shout and then fall silent. Tidal streams can hang as faint X's around a disk, then fade as the stars scatter. Even the distant arcs are not pictures in a book, but light routes, bent by a geography that changes as clusters grow and merge. The magnifying trick the clusters give us is a gift in more ways than one. It doesn't just brighten what's behind, it distorts and delays. Light that takes different paths around the lens arrives at different times. If one of those lensed galaxies hosts a star that flares, the echoes of that flare can appear in multiple arcs, months or years apart. A natural lab for measuring the expansion of the universe, a clock made of gravity. In some lucky arrangements, lensing turns a single distant supernova into a quartet of images, each a small theater showing the same play with a slight delay. The geometry we solve to make sense of those echoes ties back to how mass is arranged in the lens itself, sharpening not just our view of the past behind the cluster, but our understanding of the cluster's present. Zooming between scales can feel like stepping across stones in a quiet river. A big, smooth elliptical orders the water around it. A spiral crosses the current with two bright arms. A ring blooms from a blow. An ultra-compact dwarf hums at the edge of a larger light. The names help us talk, and then the names blur, because the sky is untidy by design. That untidiness is where the learning lives. We misunderstood galaxies for so long, not out of neglect, but because we lacked the right kinds of light, the right baselines, the right patience. Lensing taught us that mass draws maps in the air. Infrared eyes lifted the curtains. Radio ears traced the paths of electrons along magnetic rails. X-rays and gamma rays marked the shock fronts and the accelerators. Parallax and proper motion gave depth to our flat drawings. With enough overlapping maps, the edges sharpen and the emptiness between the knowns gets smaller. Return, for a moment, to the little surprises hidden in the corners of big frames. A compact dwarf near a giant tells a story about stripping and survival. A faint X of streams around a disk speaks to old meals. A ring says impact without apology. A penguin leaning over an egg is an accident of perspective and a testimony to tides. A dwarf starburst reminds you that even the smallest rooms can hold thunderstorms. A triple merger shows you how the web guides its traffic. None of these is really an exception. Each is a reminder that galaxies are not clocks wound at birth to tick the same way forever. They are communities shaped by weather, appetite, and chance. There's comfort in letting the physics come forward like a tide rather than a lecture. Gravity curves the stage, so light takes a graceful path. Gas cools and collapses, so stars line a ring and then explode, and their remnants seed the next round. Magnetic fields thread through disks and help carve out jets. Shocks recycle energy into fast particles. Those particles write in radio and gamma ray along their way. Old stars redden, young stars glare blue. Dust makes silhouettes and then glows when warmed. If you listen long enough, if you give your mind permission to idle like a boat at anchor, the patterns become familiar as weather fronts, squalls, clearings, and the fear of not knowing softens into the pleasure of watching. It helps to keep a hand on scale. The arcs in a lensing cluster can be the stretched light of galaxies, a billion light years behind the lens, which itself is billions of light years away, while the foreground stars with their pretty spikes sit in our own spiral drifts, not far at all by comparison. In a single image, time stacks like leaves. The structures we call peculiar often happen on time scales you could describe in millions or tens of millions of years. Short hours against the age of everything. And yet, those short hours can change the habit of a galaxy for a very long while. Starburst rings fade, tidal tails thin, compact dwarfs slide on as embers. Our words are clumsy because we live on the quick end of the clock. The large-scale picture, the filaments and voids, the superclusters like Hercules, the quiet dark of the boat is void, keeps the small scenes in context. Matter gathered along the web because gravity had time to work. The web's nodes grew clusters. Clusters, 8 galaxies. Galaxies, 8 smaller galaxies. The smooth, dustless ellipticals in cluster centers are not simply born smooth. They are made smooth by a lifetime of mergers and the steady stripping of the stuff that makes messy, patchy features. Farther out on the filaments, spirals held their gas longer, spun quieter arms, waited for their own busy evenings to arrive. To walk the web in your mind is to accept that stillness and bustle share a border and trade places. A last glance back at the lensing arcs. Their grace is functional. Because the mass of the lens deflects light, it magnifies not just the brightness, but the angular size of background features, letting us resolve structures we could not otherwise see at those distances. Tiny galaxies at high redshift become just large enough to study their clumpy star-forming knots, their outflows, their dust. In a universe that hides its baby pictures behind time, gravity gives us an album with a few photographs enlarged. We build the rest of the chronology by comparing what we see across time, the bright, loud quasars of youth, the quieter centers of middle age, the faint, red, quiescent galaxies settling into long twilight. When the night is this full, it's easy to feel small. Let the feeling be gentle. Small does not mean uninvited. We live in a quiet spiral where the central black hole is dozing, where dust makes pretty streaks in the Milky Way's mid-plane, where a thin disk of young stars seems to thread the bulge. where open clusters dissolve into the field and globulars circle like old ships. We are far from the ring galaxies lighting up their perimeters, far from the triples about to merge, far from the giant arcs that lens other ages into view. And yet the same rules hold. Gravity is local and universal. Light remembers. Dust speaks softer and infrared. Blue stars live fast. Red stars keep the lights on. The stories in the deep field and the stories at our door differ only by scale and by how quickly the letters arrive. You could end here with a catalog, but the mind seems happiest with a walk. Start at the arc near the cluster's center and follow it around. Imagine the path the light took. Drift outward to the smooth elliptical and sit a moment with its age. Step to the spiral nearby and count the arm segments where starbirth pricks them with blue. Notice the tiny knot to the side, the ultra-compact dwarf with its crowded heart. Move to the ring, where a spiral took a punch and turned the blow into a hoop of fire. Visit the eye, with its star-forming iris, and the faint X's of older meals still visible in the air. Smile at the penguin and its egg, and at how a tug can look like a beak. Pause in the dwarf starburst where there's hardly a dark patch to rest your gaze. Glance toward the trio, about to share futures in a thicker part of the web. Then step back until the whole field becomes one patient shimmer, 10,000 cities keeping their own times. Some nights, the sky gives us permission to leave questions open. How exactly the streams around NGC 1097 unraveled, whether the compact dwarf beside M60 truly carries the core of a larger ancestor. How long the ring and the collision will stay bright before its new stars age and redden, when the triple in Hercules will finally touch. Which distant dots in the lensed background will become the first mature spirals? The right posture for these is not urgency but curiosity held lightly. We know enough now to ask better, and we have instruments ready to answer in new ways. Infrared maps that pierce the dust, radio arrays that measure motion in the faintest gas, time domain surveys that catch things in the act rather than after each a lantern you can hang in a room you've only just unlocked. Let the lanterns glow while the universe turns at its unhurried pace. Early light passes through natural magnifying glasses and arrives with its edges warped and stories enlarged. Quiet ellipticals shine without scars. Peculiar shapes catch our eye and teach us to love asymmetry. Tiny galaxies shout, huge ones listen. Clusters bend light and host old giants. Voids hold calm like a deep breath. We used to misunderstand much of this because we were standing in the hallway drawing the house from memory. Now, with patience and warmer eyes, doors are open. The map is still a sketch, but it's an honest one. And as you set the picture down and close your eyes, you carry the feel of it with you. The arcs and rings, the smooth and the strange, the web and the quiet, like a soft melody that keeps time with your breathing as you drift. Let the picture dim to ember glow. We've walked the quiet roads tonight through Gaia's patient star-by-star map, Vista's warm eyes through dust, the thin ribbon of young Cepheids crossing the bulge, the old RR Lyrae keeping time at the core. We traced how spirals hold their shape in slow-density waves, how dark halos steady the outer lanes, how collisions can ring a galaxy like a bell, and how small clusters and ultra-compact dwarfs carry fossils of long-ago meals. We listened to a nearby microquasar for hints about distant lighthouses and watched gravity bend light into arcs that lift the veil on the early universe. All of it adds up to a softer truth. The Milky Way and every galaxy we love from afar is not a diagram, but a living weather fronts and clearings, elders and newborns, memory, and motion. Understanding doesn't end the wonder, it tunes it, like a melody settling into a slower key. Let your breath follow that tempo. Let the arcs and rings, the smooth and the strange, drift to the edges of thought. The map will keep filling in while you rest. For now, close the night gently around you and keep a small part of the sky quiet, warm, unhurried, glowing behind your eyes as you slip into sleep.